In this video lecture for our severe and hazardous weather course, I want to focus on water in the atmosphere. So let's look at this map. It shows the last 30 days of accumulated precipitation through early in the morning on September 11th. This fall, we've had two massive, powerful hurricanes that made landfall in the United States, within a month of each other. First, we had Hurricane Harvey come through parts of Texas and Louisiana, dropping in some locations up to 50 inches of rain. 50 inches of rain. Even in parts of Tennessee and Kentucky, Harvey, the remnants of Harvey, dropped better than 7 inches of rain. This is an enormous quantity of water to be falling from the atmosphere. Then Hurricane Irma went right up the north-south kind of direction here of the Florida Peninsula, in some locations dropping better than 25 inches of rain. And while all of this is going on the eastern half of the country, the western half of the country, some locations in the Pacific Northwest have not seen precipitation for more than 70 days. And as a consequence, we've had massive forest fires that have broken out in the Pacific Northwest. Well, we need to talk about water. We need to talk about its distribution in the atmosphere and how it falls as precipitation, as snow, as rain, and how we can have some incredibly extreme events like massive flooding events followed by prolonged drought. Basically, it is the abundance or the lack of water that create our planet's most expensive and most costly in terms of human lives, natural disasters. So let's dig into this. Now, one of the cool things about Earth's atmosphere is that the only substance in Earth's atmosphere that naturally exists in all three phases, that's a solid, liquid, and gas, is water. In fact, it's pretty amazing. Earth is the only planet that we've discovered so far that kind of has that property. Now, I think you're all familiar with the three phases of water. Okay, everybody has seen liquid water. I mean, we have to drink it every single day, so this is no surprise. Also, down here we have ice. Let me show you. There's something really cool about ice, and that is this. Every ice crystal at its molecular level creates a bond with other water molecules such that those bonds align themselves to make a six-sided ice crystal. And so that's why all ice at the molecular level is a six-sided crystal. And that also is the reason why ice crystals, as they continue to grow off of that initial ice crystal, tend to have six sides as well. So that's why we often draw snowflakes with six sides. Well, anyways, one neat thing about liquid water and solid water is that liquid water is the most dense phase of water. Okay, that's why ice floats when you put it in a cup full of water. But what I really want to stress in this video is I want to talk about this top image here. You see, I've got it labeled next to water vapor. But what you're seeing in this, what's coming out of the top of this very hot cup of coffee is not water vapor. In fact, you can't see water vapor. And as I zoom in there, you can see that what we're looking at here are tiny little condensed liquid droplets of water. What I want you to take away from this is water vapor is invisible. So I got a few examples here. We've got this guy here whose head is clearly steaming. We have a bunch of exhaust coming out of this tailpipe. We have some massive cooling towers producing this huge cloud. And then I've got this bird that apparently is breathing, and you can see the water vapor. Not the water, you can see the water. That's an important distinction here. Every single thing that you see in these images is condensed liquid water. You're not able to see water vapor. Water vapor is a gas, and we cannot see gases. Therefore, you're seeing condensed liquid water in each case. So keep that in mind as we move forward throughout this lecture. All right, let's talk about beer and beer koozies. Most of us here in the United States, when we drink beer, we like our beer really, really cold. In fact, the Coors Company makes a beer can such that the mountains on the side of the can turn blue to let us know when it's cold enough to drink. So we've invented this thing called the beer koozie that goes around the beer. And the idea here is to protect that beer and insulate it and prevent it from getting warm. But I want you to know is that this particular instrument here, the koozie, this device, not only prevents your beer from getting warm by preventing you from conducting heat from your hand into the beer through the glass, but it also insulates the glass from condensation. You see, every time you see a glass of a cold beverage sweating, in other words, we have water vapor condensing on the side of it, there's a heat transfer. And that heat transfer is putting heat into the glass and into the fluid, helping it to continue to warm up. And that's a very, very important point that I don't want you to forget about water vapor. Because water can exist in all three phases in Earth's atmosphere, it will readily change between them. And vast amounts of energy are exchanged when that happens. So a couple of simple things about water. Let's start on this side of our graph here. Remember, water vapor is a gas, and because our eyes cannot see individual molecules, when they're separated, we can't see water vapor. That's the least dense phase, but it's also the highest energy phase of water. When you look down here, we have the ice crystal and structure inside of this square, and then we have the liquid water structure inside of this square. And you can see we can pack more water molecules in there than we can for ice, and that is why ice will float in liquid water. And I believe it's one of the only substances that we know that will do that. I believe silicone might as well, but water is one of the only substances that displays this property, where the liquid is the most dense phase. But what I really want you to take away from this slide is this graphic in the middle. I'm not so concerned that you memorize, that going from a liquid to a gas is evaporation, and from a gas to a liquid is condensation, and we have melting and freezing. And then remember, you can skip phases. You go from a solid to a gas without becoming a liquid. We call that sublimation. And from a gas to a solid with skipping the liquid phase is called deposition. What I want you to see are these arrows on the outside. As you go up on this diagram, from a solid to a liquid to a gas, energy must be absorbed in order for the phase change to happen. Go the other direction, go from a gas back down to a solid, that same amount of energy is released. And we call this energy that's used to create a phase change. In other words, going from a solid to a liquid, or liquid to a gas, or any other direction on that graph, we call that latent heating. It's the heat associated with the phase change. I want you to understand something. When we talk about water, there's enormous quantities of energy that is exchanged when we change phase. Here's a fun way to think about it. I'm teaching the class this semester in Lincoln Hall Theater. And if I were to perform a little experiment in there, I brought in a heating element and I brought in a pot like this and I filled it with 1 gallon of water. If I evaporated all of that water by simply just putting it on the burner and allowing it to boil off, all that water vapor would then occupy the air, would mix with the oxygen and nitrogen in the theater. But check this out. If in an instant I condensed all of that water back into the pot to become a liquid again, the amount of energy released would completely blow Lincoln Hall apart. There is, in every single gallon of water, around 4.7 sticks of dynamite worth of energy. And we can experience that when we evaporate it and condense it. So some things to remember here. Evaporation is a cooling process. Condensation is a warming process. So think about it. You ever gotten out of the shower and not had a towel nearby? And you go running down the hall to the closet to get one? As you're running, the water's evaporating off of your skin, cooling you down very, very quickly. By the same token, if that sweat doesn't, evaporate, you feel really, really hot and disgusting, or if water doesn't evaporate off your skin. And just as you learned with the beer koozie example, condensation is a warming process. Now, to make sure you get how much energy is associated with the phase change of water, I want you to watch this video. What we're looking at here, this takes us back to the end of World War II, and you just saw one of the first of 2 nuclear weapons that were used on Japan. Now, this is an integral and important part of world history. But here we are on August 6th, seeing a 15-kiloton nuclear bomb called Little Boy dropped in Japan. And just a few days later, here's the second of these 2 bombs. Now, this particular bomb called Fat Man was a 21-kiloton bomb. Very, very powerful. And I'm showing you this because often in physics, we like to compare energy amounts to the energy released in these bombs. So let me take you here. This was in 2005. Up to this point in history, when I made this video, you are staring at the United States' most expensive natural disaster ever. Somewhere between $160 and $200 billion were spent cleaning up after Hurricane Katrina made landfall in Louisiana, Mississippi. What you're seeing here is just a day before landfall. Inside of this eye were 175 mile per hour winds. I don't care about the energy associated with the wind of this hurricane or the waves that it produced or the rain that it made. If you look at just the amount of energy that formed when making these clouds, or that was released, I should say, when making these clouds, that was energy that the sun used to beat down on the surface of the ocean, causing the water to evaporate, and then it condensed again to make these clouds. This hurricane, in one day, released around 200,000 Fat Man bombs worth of energy. And this hurricane was around for well more than a week. So it's important for you to understand that our atmosphere, through the phase change of water, releases vast, vast quantities of energy. And that is how these things become so powerful. It's the uniqueness of our atmosphere to have a temperature range such that we can support water vapor, liquid water, and ice all at the same time. So let's take all of this and do something kind of fun with it. This is a animation here showing you water vapor and where it is kind of positioned all over the planet. Now, you can't see the country boundaries, but you can start to see where they are. For example, here is India in the Himalayan mountains. Here's the United States and Mexico. Here's the Andes Mountains. In fact, this region right here is the driest region outside of the polar regions of our planet. It's called the Atacama Desert. The desert in here is basically between two huge mountain chains, and in that valley in between, because all the moisture is blocked, there are some locations in here that we put meteorological weather stations that have never observed precipitation over decades. In fact, there are some stream beds here that have not seen precipitation and have not had flowing water in them, we estimate in about 120,000 years. In March of 2015, a freak thunderstorm hit a community just outside of the area that I was just telling you. That thunderstorm produced nearly 11 years worth of rainfall in about 30 minutes. And all the rain that it produced was 9/10 of an inch of rain. Now, contrast that with Hawaii, or this location over here in India called Cherrapunji, India. You know, the big island of Hawaii, the mountain range of the front range of the Himalayan mountains here. Some of these locations can get better than 500 inches of rain in a year, simply because of the way water vapor is moving throughout the system. Now, I want you to remember one other thing about this animation. The driest places on Earth are actually our polar regions, and that's because of this fact. The atmosphere's ability to contain water vapor is directly proportional to its temperature. So that means the hotter it becomes, the more water vapor the atmosphere can contain, meaning that the Earth's equatorial regions can contain the most amount of water, whereas our polar regions, which are cold, contain the least. Keep that in mind as we move forward here. Now, this is Shrek, a great story about this sheep. All right, this particular sheep was found, I guess it was lost for about 6 years. And over that time period, it was never shorn. In other words, it never had its wool cut off. And it turns out when they finally found it, amazing that it survived. It couldn't even see, okay? When they found it, they were able to take off of this thing 90 pounds of wool. That is enough wool to make, as you see down here, 20 separate men's suits. Incredible. I bring this up because of a very famous man. His name was Nicholas de Cusa. And a long time ago, this guy was a scientist and an inventor and a very important kind of figure in history. But one of the things that he did was he had a bunch of sheep. And he learned that he could make more money off of the wool that he was selling from his sheep if he sold it at market on days with very high humidity or days that it was raining. And the reason why is because wool, very similarly to human hair, absorbs water vapor. So he could actually sell the wool, which was sold by weight, and get more money for it by selling on days when it was humid, because the wool would weigh more because it has then absorbed that water vapor. Well, anyways, let's move this to one of our early primitive instruments we used to measure water vapor. It's called a hair hygrometer. Many of you that have long hair probably know that when the humidity changes rapidly, especially if you are Caucasian and have Caucasian hair, that tends to be the biggest or the most prominent type of hair that responds to changes in humidity, at least that we've studied. Well, you've probably noticed that your hair gets curlier. It changes in its texture and shape as humidity changes. Well, it turns out some of the early instruments, which you're seeing here, a hair hygrometer, that we used to measure moisture was using human hair. And underneath this little shelf here, you can see we've got some basically hair that's stretched between these two clips and a little clamp there. When the humidity increases, the hair lengthens. And if the hair lengthens, it basically changes how this little arm here moves up and down with a little marker on it and changes the humidity throughout the day. Now, I know that for a lot of people, when the humidity gets high, as the hair lengthens, it actually curls as well. But we've eliminated that impact by stretching it between these two clamps. So this was a primitive way by which we could measure the amount of moisture in the atmosphere. Now, thankfully, we don't do it this way anymore. We, of course, have much more sophisticated instrumentation. We use things like chilled mirrors or hygristors, which are very small circuits that are responsive to changes in humidity. But this was one of the primitive ways in which we did that. Well, here comes the science behind all of this. When we look at the amount of moisture that's in the atmosphere, we have to remember that it's mixed up with dry air. So I have this cylinder here that you're looking at on the slide, and all those red dots there represent the dry air, the oxygen and nitrogen. And inside of that, we have some water vapor that's mixed in as well. What we need to be able to do in atmospheric sciences is we want to be able to separate the dry air and its mass from the water vapor and its mass. Because ultimately, I want to know exactly how much water vapor is in the atmosphere at any given time. Because so much energy is released or consumed in its phase change, knowing how much is there at any given time helps me understand what the atmosphere is capable of doing in terms of producing hurricanes or massive thunderstorms or the lack of both, which leads to huge drought. So let's talk about measuring this important quantity called vapor pressure. Now we've already learned about pressure. We know that pressure is basically the collision force of the air in the atmosphere. It's pushing, okay? We're trying to now separate out the collision force, the pressure, the partial pressure of water vapor. And we're going to do that by coming up with this term called vapor pressure. It's the force per unit area applied only by the water vapor. If you need to think of it of another way, it's like this. And here's our ultimate problem. You know, your full pressure that you push down on a scale when you weigh yourself is basically the sum of all of your body parts. You see, what's tricky about measuring water vapor is I'm trying to extract the partial pressure of one gas. But the only way I'm able to try to do that is by measuring the mass of all the gases, or the pressure of all the gases. It's like me having you stand on the scale and say, just measure the weight of my intestine. That's nearly impossible. And because of that, we have to measure vapor pressure with a proxy measurement. And the way that we're going to do that, the way that we're going to find the partial pressure, in this case, of moist air, so I got a total pressure of 1,015 millibars. Well, maybe the moist air contributes 15 millibars. Well, that's the vapor pressure. I need to know what that is. How I'm going to find it is by using this term called the dew point temperature, something you've heard a lot about. The dew point temperature can be measured. And what we're going to do is we're going to find a relationship between dew point temperature and vapor pressure so that I can ultimately back out that value of vapor pressure. So we're going to come back to that in just a few moments here, okay? So remember, we want to find the vapor pressure, which is the partial pressure exerted by water vapor. But to get it, I got to measure something else called the dew point temperature, a more common term that you've heard. Now, the second thing I want to show you here is this video. Check this out. Pretty incredible, right? You just saw this massive tanker implode on itself. Watch it again here. Amazing to see something like that. And I don't know why we have to have the music in the background, but it's there. Let me mute it and let's watch it again. What's going on here? We see this tube. They're pumping this thing full of steam. And on this particular day, what's going on is that the rain is falling on this huge tanker, and that rain is cooling the surface of the tanker. Well, the steam, the water vapor on the inside of this, as you cool the atmosphere, well, it must condense, which means it's going to go from a vapor occupying a large volume to a liquid occupying a small volume, thus reducing the internal temperature of the tank. The moment that happens, the atmosphere comes crushing in on the outside of this, and you can see what it does to the tanker. This is just proof so that you can see that water vapor does exert a partial pressure, because when it was removed by condensing the water vapor to make a liquid, well, that removal of that pressure meant that the outside air pressure vastly exceeded the internal pressure of this tank, and thus it came crushing inward just like that. Well, to understand water vapor and its partial pressure in the atmosphere, we need to talk about something called the saturation vapor pressure. The saturation vapor pressure is just this. It's the vapor pressure when you've completely saturated the atmosphere with respect to the amount of water vapor it can contain. So basically, as you see in this bullet point, it's the saturation point of the air with respect to water. And as I told you, it's a function of temperature, and that's what this figure down here at the bottom says. The big bullet point is what you see down here at the bottom. It says this: air has a finite, call it holding capacity, for containing water vapor, and that depends on temperature. It's an exponential relationship, which means that as you increase temperature, the amount of water vapor that the atmosphere can contain increases exponentially. We measure that, again, in millibars, a unit of pressure. Now, when I was a kid, I took my first high school physics class. It was a very simple experiment. My high school teacher, Mr. Butcher, gave everybody a beaker of water. He gave us a little container full of sugar and a spoon, and he also gave us a Bunsen burner. Now, what was neat was we were told to put the spoonfuls of sugar into the water and try to get them to dissolve. Well, you could put in a few spoonfuls and stir it up, and the sugar would dissolve and become a part of the solution. But eventually, you'd put in some sugar, and it would go into the water, but not turn into solution. It would stay as solid sugar crystals at the bottom. I was asked, well, how do you get rid of them? How do you get them to dissolve? And the answer was, put them on the Bunsen burner. Heat the mixture up so that it can contain more dissolved sugar. It's the same thing with the atmosphere. The hotter it becomes, the more dissolved water, which we would call water vapor, the atmosphere can contain. Now look at the picture over here on the right-hand side. I've got a building here extending into the clouds. See if these relationships make sense. Up here, my atmosphere is completely saturated with water vapor. In fact, it goes beyond a humidity of 100% because I'm condensing some of that water out. But when we reach a relative humidity of 100%, what that is telling us is that the total amount of water vapor, as measured by the vapor pressure, equals its saturation point. Therefore, you get condensation. Down here, I don't have that. The air is not saturated. My humidity is less than 100%, and therefore the amount of water vapor in the atmosphere, as measured by the vapor pressure, is less than its saturation point. You see, I bring up these two things because when we talk about these values of vapor pressure and saturation vapor pressure, I do it for a reason. And that's because those two values are used to calculate what is most likely the most confusing term in all of atmospheric sciences, relative humidity. It's a term we all use all the time, but it's very confusing. Let's come back to these two terms, dew point temperature and relative humidity, and understand how vapor pressure and saturation vapor pressure work together with them. So here we go. What's the definition of the dew point temperature? It's simple. It's the temperature to which you got to cool the air to get dew to form. So imagine you're sitting in a room right now watching this video. If you wanted to experience the dew point temperature, go over to the thermostat and crank the temperature down as low as you possibly can. If your dew point temperature is within the range of temperatures that your thermostat and therefore your air conditioning system can handle, you can actually cool it off enough that you saturate the air in the room and you start to get condensation. Well, what's condensation? Well, it might make dew. It might make a fog. It might make a cloud, or it might make frost. This is us converting water vapor into a solid like ice or into a liquid like dew or fog or a cloud. So that's what the dew point temperature is. It's the temperature that you have to cool the air to get condensation to form. In other words, most nights when the temperature drops off and all of a sudden dew begins to form on the grass, we've cooled the air to the point that near that blade of grass, it's saturated. So the liquid water comes out of the atmosphere by the form of condensation. Okay, I think we get the dew point temperature, but let's talk about relative humidity. Relative humidity is a measure, as you see here, of the actual amount of moisture in the atmosphere relative to its capacity. Now, given that definition, it should make sense that the equation is this. All we're going to do is take a ratio of our vapor pressure over our saturation vapor pressure, how much water vapor is in the atmosphere in the numerator, and the capacity for water vapor in the denominator. Now, to make sure that this makes sense, I've got over here a parcel of air, kind of outlined it in a circle. What determines the total available space in that parcel of air for water vapor to exist is its temperature. So for example, at this given temperature, we'll just make up a temperature here. Let's just say the atmosphere has these spots, 12 spots, in which water vapor can live. Let's think of it in this way. If I fill 4 of them, I've basically saturated 33% of my available places for water vapor to exist. And all I did here is I said, well, let's let my vapor pressure equal 4, my saturation equal 12. I've got 4 out of 12 full. 4 divided by 12 times 100 equals 33%. Now, if I want to change relative humidity, I can do these things. I can heat up the air. If I heat it up, I basically provide for more spots. See that there? More spots for the water vapor to exist. If I cool it off, I get rid of those. If I cool it off, the relative humidity goes up. Warm it up, the relative humidity goes down. I can also put more water vapor into this. I can evaporate it from the ocean surface. I could breathe into it. I could just add water vapor. And if I do that, I can fill in more of the spots, thus increasing the relative humidity. You see, what's so confusing about relative humidity is it's relative. And pay close attention to this. It's relative to both the amount of water vapor that's currently in the atmosphere and the amount that the atmosphere can contain. And primarily, these two things are related to dew point temperature and temperature. So what I mean by that is you live right now, because you're watching this video and you're taking my class, in Champaign. And I'll tell you, the relative humidity is a useless term for you in Champaign. You may want to use it as a way to kind of guide you in maybe your comfort level in any given day. But here's what I mean by that. Because Champaign's temperature varies so much throughout the year, the relative humidity is a poor measure of the amount of water vapor that's in the atmosphere. Here's a case in point. In the middle of winter, we could have a temperature outside that's 25 degrees and a dew point temperature that's 24. Now, when you look at that, those two values are very close to one another. And as it says up here, when temperature is close to the dew point, you have very humid air, high relative humidity. But in reality, the air is still extremely dry because cold air cannot contain much water vapor. And that's why you get sick in winter. I mean, think about it. Outside, the dew point temperature, which is a measure of the actual amount of moisture in the atmosphere, is 24 degrees. The temperature is 25. Your relative humidity is well above 90%. But there's just not much moisture in the atmosphere there to work with because the dew point is still a low value. What happens is we suck that air into our heaters. The air comes into the room where we crank up the temperature, which increases the SVP, the saturation vapor pressure, but we don't add water vapor to it. And as a consequence, this ratio goes way down, and we breathe in all winter long extremely low humidity air. And the problem with that is that when we breathe that in, it dries out our throats, making them more susceptible to infection. And that's a big reason why you get sick all winter long. You're breathing really dry air. I tried to combat that in my house. You see, when I put in a new furnace this past year, I actually went in there and put in a whole home humidifier so that I'm continually putting water vapor, raising the vapor pressure in my house so that my kids don't get sick all the time. So you want to prevent getting sick all winter? Put a humidifier in your room. Pump in that water vapor. It moistens the air. It makes it easier for you to breathe, keeping your air passageways basically wetter, preventing you from getting infection. Now, that's not the only thing that makes you sick, but that's one primary thing. So that's certainly something to be thinking about. Now, let's do some practical examples here to make sure that you understand how this works. I got a series of questions, and I got 4 cities we want to look at here. Bismarck, temperature 35, dew point 34. Chicago, 55 temperature, 45 dew point. Miami, 86 with a dew point of 68. And Phoenix, 101 with a dew point of 59. Let's answer these questions together. Let's see if this all makes sense. Okay, I want to know which city has the highest relative humidity. Well, we're not going to be able to do a quick calculation of vapor pressure and saturation vapor pressure, but what we can do here is we can just look for the city with the closest temperature to the dew point, and that is most certainly Bismarck, 35 and 34. Which city has the lowest relative humidity? Just look for the biggest spread. That is most certainly Phoenix. So I think those first two are pretty easy. Let's see if this lecture's sunk in, though, so far. My next question is, which city has the highest saturation vapor pressure, SVP? All you need to remember is this. The atmosphere's ability to contain water vapors proportional to temperature. It's an exponential relationship, which means the hotter it gets, the more water vapor the atmosphere can hold. Doesn't mean it has to, but it can. Therefore, if I'm looking for the city with the highest saturation vapor pressure, it's easy. Look for the hottest city, and that is Phoenix. Now, which city has the highest vapor pressure? Well, just like saturation vapor pressure is related to temperature, vapor pressure is related to dew point temperature. City with the highest vapor pressure is also the city with the highest dew point. In that case, it is Miami. Now, these last couple of questions I'm going to ask you are going to get a little more tricky. My next question is, which city has the highest moisture content? Which city has the highest moisture content? As you're thinking about that, you may be tempted to think Bismarck, because we know it has the highest relative humidity. But remember, Bismarck has a very low temperature, which means it's cold. Cold atmospheres, cold regions like this, are very easy to saturate. That's because the atmosphere can't contain much moisture. If I ask you which city has the highest moisture content, don't go looking for a cold city with a high humidity. Look for the city with the highest dew point. Remember that the dew point temperature is the measure of the absolute amount of moisture in the atmosphere. So Miami also has the highest moisture content. Now, let me hopefully not confuse you with this next statement. Bismarck's relative humidity is above 90%. Phoenix relative humidity here is very, very low. So what I want you to know, though, is that in Phoenix, Arizona, on this day when it's 101 degrees with a dew point of 59, compared to Bismarck, North Dakota, with a temperature of 35, dew point of 34, very high relative humidity in Bismarck, very low relative humidity in Phoenix. But listen closely. There is more water vapor in the atmosphere, in the air over Phoenix than there is over Bismarck. And that's because Phoenix has a higher dew point temperature, which is the measure of the actual amount of moisture in the atmosphere, compared to Bismarck. Cold atmospheres are easy to saturate. Don't forget that, okay? So always in winter in Champaign, we have really, really high humidities, simply because it's cold here during winter. But that doesn't mean there's a lot of moisture in the atmosphere. Keep that relationship kind of straight in your head. What's my last question is which city would sweating be the most and least efficient way to cool off? Well, you're only going to sweat in this case in Miami or Phoenix. It's a beautiful day in Chicago. It's really cold in Bismarck. You're not going to sweat in either of these two cities. Well, between Phoenix and Miami, think about it this way. The sweating would be most efficient in Phoenix. Why? Well, this huge difference between the temperature and dew point means low relative humidity. And that low relative humidity means that there's plenty of room in the atmosphere for which water vapor to evaporate off your skin, such that it goes into the atmosphere without any problem. That's why old people want to live in Phoenix. It's a dry heat. It's comfortable. Miami's a different story. The humidity level is relatively high, but there's tons of moisture in the atmosphere. Miami is not a location where sweating is efficient, and that's because there's not much room left, because the dew point and temperature are close to each other and there's high heat here, to get that sweat to go somewhere. So that's why it's often very disgusting in Miami in the middle of summer. So that's a couple of our practical examples. Let's take this one step further. I'll never forget the summer of 2012. Here's the quick story. I lived in Champaign. I had one neighbor on my east side who decided that he needed to, on the first kind of warm day of March, to go out and kill with Roundup all of those little violets that spring up in the yard. He actually wanted to do this to my yard as well. Comes over, pounds on my door at 9 a.m., said, "Hey, Eric, I'm going to go out and take care of some of the weeds in my yard. I don't like those little violets." He says, "I'm going to go spray them." He goes, "You want me to do your lawn?" I said, No, don't touch my grass. So he decides to go over his grass, and I wake my wife up and I say, "Elena, I think the neighbor's about ready to spray Roundup on his grass." Now, if you don't know anything about Roundup, it kills grass. And sure enough, this guy covered his entire lawn with Roundup, and just a couple of days later, his entire lawn was dead. Now, if you know nothing about 2012, or have you forgotten about it, there was a massive drought in the central part of the United States in 2012. And this guy, who had to completely repair his lawn all summer, spent over $10,000 trying to repair it, all because he decided to put down Roundup. Now, the neighbor on my west side, I'll never forget this guy either. He was pissed off at me all summer long because my lawn looked so much better than his. And that was because I knew something very important about this graphic that you've been looking at here for the last couple of minutes. I know when to water my grass so that it stays green even in nasty droughts. My neighbor didn't. His lawn turned brown. Mine stayed a beautiful green. I know some of you don't care about this, but when you get a house, you start to care about what your lawn looks like. Well, anyways, what I did was I watered my lawn overnight. I would go to bed midnight, 1 o'clock, and I'd water right before I go to bed. Sometimes I'd wake up really early and water it. Now, why would I do that? Well, I did that because of this graph. Midnight to midnight on the x-axis. This line is dew point temperature. We're just saying that we're going to keep the dew point temperature constant. Now, if you know anything about temperature, usually our coolest temperatures are right before sunrise. And the temperatures warm throughout the day, reaching a peak in mid-afternoon before the sun begins to set and the temperatures cool off. Because relative humidity is basically related to the dew point temperature and the temperature, the closer these two lines are together, the higher the humidity. The farther apart they are, the lower the humidity. Well, when you have low humidity, evaporation happens easily. When you have high humidity, evaporation is difficult. I watered my lawn overnight or early in the morning so that when I put the water down, it would soak into the ground and be used by the grass later on in the day when the humidity was low and the temperature was high. My neighbor Don, on the other side, he would always go out and water his lawn in the afternoon. One day I walked out to him and said, "Don, listen, when you water your lawn in the afternoon, Better than 60% of the water that you put on the grass evaporates immediately in this high heat. Therefore, it's not even used. So he switched his strategy toward the end of the season and watered overnight like I did, and his lawn looked fantastic. Now, for completeness, my neighbor across the street was completely crazy. Through the entire summer of 2012, this massive drought and heat wave summer, this guy placed his sprinkler system in the middle of his driveway and kept his driveway wet, and his lawn was destroyed. I don't get it, but welcome to living in a neighborhood. Okay, that's enough. Now you know when to water your grass. Overnight, early morning. That's the best time. Let's do another example. Ever got in a hot shower and want to see yourself in the mirror but can't see yourself? Well, let me tell you, here's one of the most effective ways to remove the condensed water vapor, that's liquid water, that's formed on this mirror. Why is it there? Well, when you got in the shower, hot shower, you put a ton of water vapor into the air in the bathroom. The mirror, being a cold surface, serves as a surface onto which the water vapor condensed. That's because we cooled the air right next to the surface of the mirror, and that lowered the saturation point of the atmosphere right there, thus supersaturating it, causing condensation. Now, you want to get rid of this. So how do you do it? Well, some of you might take a towel and wipe it off, and that's part of the solution, or you might turn on the bathroom vent. When you turn on the bathroom vent, you're going to draw out that very high humidity air and reduce the vapor pressure, thus promoting evaporation. But that's not usually very effective. Some people like to open the door. Opening the door does the same thing. You let in some drier air to mix with that humid air, thus lowering the relative humidity. But I know a few people that are pretty brilliant about getting rid of the water vapor that's condensed onto the mirror. And that is, they get out a hairdryer. And that hairdryer they then blow against the mirror, and it has kind of a double whammy effect in removing the condensed liquid water on the mirror. Think about it. By blowing the hot air onto the mirror, we're warming the mirror's surface, therefore increasing the saturation vapor pressure, the denominator of our relative humidity equation. By doing that, humidity automatically goes down. Plus, the hairdryer is also drying the air out as the air passes through it, lowering the vapor pressure. You basically have a double whammy effect on reducing relative humidity, and it clears the mirror very, very quickly. So that's a helpful hint. Blow some hot air on that sucker, and it will clear off. Let's see if you can apply that same idea to this situation. Imagine you're driving in the car and you're sitting in there with 10 of your best friends, okay? And it's raining outside, so you have the windows up. Well, all 10 of you are sitting in this small car breathing, and that water vapor you're putting into the atmosphere of the car is condensing on the inside of the colder windshield. Well, how do you get rid of it? Well, the simple thing is blow some air on it. But here's the question. When you turn on the vents, do you blow hot air onto it, or do you blow cold air onto it? Think about it. Just like the situation in the bathroom, you want to turn your vent temperature to high heat. Why? When you blow hot air, you're blowing high saturation vapor pressure air, thus increasing the denominator of that equation for relative humidity, thus evaporating the water that's condensed on the inside of the mirror. Now, if your car doesn't have a functioning heater and the vents don't work, roll down the window. Unless you're driving in a fog, the humidity on the outside is lower than the humidity on the inside, and thus it'll clear off your windows. And also, always leave your vent on recirculate in this situation. You don't want to keep recirculating the high humidity air that all of you have breathed into the car. Remember, though, stopping breathing is not a solution to this problem, but that would certainly get rid of it as well. Now, there's one last thing. In my car, when I automatically turn on the window defroster, which is going to basically blast hot air onto the window, thus evaporating the water vapor that's condensed there, my car also automatically turns on the air conditioner. Now, a lot of people think that air conditioning only happens when you cool the air, but that's not true. Air conditioning is the removal of water vapor and the change of temperature. So what happens is my car turns on the heat and the air conditioner, and it's again a double whammy effect. The air conditioner removes the water vapor from the air in my car, and it blows that hot dry air onto the window, thus removing the water vapor. So, all of these are very simple applications to understanding water vapor in the atmosphere. And you can now see that relative humidity is one of the trickiest terms. Now, one last story is this. When I was teaching this a few years ago, I had a teaching assistant. who, after I said, hey, using relative humidity as a gauge on the moisture content in the atmosphere in a place like Champaign is useless because of how much our temperature changes, well, this girl raised her hand, one of my teaching assistants, and she says, well, where I live, we use relative humidity every single day as a measure of what the atmosphere is going to be like, or how, in her case, how her hair was going to look on that day. And I said, of course you do. I said, tell the class why you use relative humidity every single day throughout the year. And she says, well, I'm from Puerto Rico. And I said, what's the significance? She says, well, in Puerto Rico, our yearly variations in temperature are small. And that means the denominator of our equation for relative humidity doesn't change throughout the year. As a consequence, relative humidity means something to her because we've removed that degree of freedom, that variability by getting rid of the temperature change. So she could go out and use relative humidity as a continual proxy on the amount of moisture in the atmosphere. But for us in Champaign, we have high humidities all winter long, yet it's dry. In the summer, we have low relative humidities for the most part, below 60, 70%, yet it feels disgusting and humid. And as a consequence, relative humidity is a confusing term to use if you live in a location that has rapidly changing temperatures throughout the year. Well, that's it for this lecture on water vapor. Hope you found this intuitive and informative. If you have any questions, shoot me an email and let's talk about it. Thanks for watching.